Okay, so welcome back. I will continue with the next part. Now, in the first part, you learned some basics about computer architecture as far as it is important for understanding the performance features. So we learned about pipelining, superscalarity, and all these motifs will return time and again in this course. So it's good that you heard it in the beginning. Now, you saw also that modern multi-core processors have a lot of topology, meaning it's important to know where in the machine a specific core or a certain part of the hardware resides. And even more important, which parts of the hardware are shared between different executing units or executing cores on the machine. We see lots of examples later. Here we have an overview of a modern multi-core, multi-socket chip. It's a two-way server, 2 sockets, only 4 cores, but imagine there were 8, and you have a modern. This is probably Nihalem type, so like 5-6 years ago, but it doesn't matter. And we have 2 sockets. Each socket has its own memory, of course, it's CC/NUMA architecture, which is the dominant architecture, as you know now. They're connected by a coherent link, so all memory transfers are routed transparently across that link if it's necessary, so it's completely done in hardware. And we have probably some GPUs connected via PCI Express, and we have other I/O resources like disks and so on. Okay, so in such a setup, in such a typical compute node, we have different types of resources. And they can be categorized into parallel resources, resources which are easy to scale or cheap to scale. So resources which can be augmented or improved more or less easily. For example, by putting the transistors to use that Moore's law gives us. And there are other resources which are shared, which are potential bottlenecks, not so easy to scale or very expensive to scale if you want to improve them. So the first easy to scale parallel resource is execution units or SIMD units. It's easy to put in more execution units. Whether it makes sense in terms of writing efficient software, getting the compiler up to the task and so on is another matter. But since we get more transistors every year, it's easy to cast them into execution units. Okay? So that's a resource that's easily scalable. Of course, we get more cores. We can put all these execution units into another core, another core, another core. Every year we get more cores. So nowadays we can buy multi-core chips from Intel with 15 cores, and who knows what will happen in 5 years' time. So cores are also easy to scale. It's just the Moore's law issue. On all modern designs today, we have inner cache levels that are private to each core. So each core, in this case, has its own level 1 data cache, its own level 2 data cache. Usually level 2 is unified data and instructions. So these inner cache levels are private. They're not shared, so they're not prone to any bottlenecks. If I add a new core, I add a new inner cache level, and then I can use the data in this cache level privately to this core, and there's no bottleneck. I can easily add sockets on your CC/NUMA domains. And that's why we have CC/NUMA in the first place. CC/NUMA means if I add a new chip, a new socket, a new memory interface, I immediately get scalable bandwidth. I get more bandwidth with every socket. And it is possible to have multi-socket systems with 4, or even 8, or even more sockets. If you've ever seen SGI systems, ultraviolet or Altix, you can have thousands of cores, essentially, in a single shared memory image. And it's, of course, CC/NUMA. So it's not that hard to scale. Of course, machines with a lot of NUMA domains are expensive, because it's not your commodity off-the-shelf system, but it's doable. It can be done. And of course, if you have the PCI slots, and if you have the power supply to do that, you can put in multiple accelerators. It's not that hard. You need a case, and a power supply, and some slots, and then you can put in 2, 4, 5, 6 accelerators if that's what you want. So easily scalable. On the other hand, we have resources which are not so easily scaled, which are potential bottlenecks. The first potential bottleneck that we see on the chip level is the outer level cache. Today, we have processors which usually have a shared outer level cache for all the cores. So this cache level is shared. It's not only sharing of the space, it's also sharing of the bandwidth of this cache. So potentially, this cache level could be a bottleneck if all cores request data from this cache. could be too slow to satisfy all the requests at the same time. Of course, the most important bottleneck on the socket or NUMA domain level is the memory bus. Memory bus is always too slow to feed the execution units. We've seen it on the second slide in the beginning, where we saw that the good code, the well-optimized code, showed a saturating behavior because it exerted so much pressure on the memory interface that the bandwidth was just not enough to keep the code scaling. Yeah? Which was a good thing in that case, because we exhausted the relevant bottleneck. If you exhaust the relevant bottleneck, that's a sign for a good code. But of course, it is still a bottleneck. So memory bus is probably the most important bottleneck. We have this inter-socket link, which could potentially be made very fast. There are and have been machines with a very fast inter-domain links. But usually, this link is much slower than the local memory interface. Whenever you have to go through this link in order to access data from memory, you have a performance penalty. We will see later how much that is usually on typical systems. We have PCI buses, and there's always a limited number of PCI Express lanes. Nowadays, the PCI Express interfaces are moving to the processor chip, so it's a part of the chip. There are enough transistors and pins to do that. So if you put in many, many GPUs, then the number of PCI Express lanes could be a bottleneck. Might not be fast enough in terms of PCI Express lanes to feed all those GPUs with the required data. And there could be other I/O resources. First and foremost, network interfaces. If you compare the speed, the bandwidth of a network interface, which is usually a couple of gigabytes per second, with the available memory bandwidth, which is nowadays close to 100 gigabytes per second, there's a mismatch, right? So this is always too slow. You could put in more network cards. You could have multi-rail, InfiniBand networks, but that only helps you so much, okay? It's always too slow. Okay, so we have parallel resources and shared resources, and the key question is, if you have an application that runs on this hardware, how does it react to all those details? How does it react to the bottlenecks and the scalable resources? Does it rely for its execution exclusively on these features, which means I get a speed up automatically with every new processor generation that gives me more cores? Or does it rely on shared resources, which means I could end up in a situation where over many years, performance stays the same? Because one of those bottlenecks is important for me, and that happens to be a bottleneck where nobody ever tries to do something about it. Okay, another thing, of course, is that this complex setup, and this is, as you know, not the most complex processor we could imagine, incurs some topology. So it's important to know where your processes and threads are running. And of course, there are many programming models you can choose from for parallel programming today. So you could, for shared memory programming, you could use OpenMP, which is probably scientific computing the dominant programming model because it's so easy to employ, or seemingly easy to employ. You could use good old MPI for intra-node parallel computation. Why not? If the program runs fine, then why not use MPI? You could use bare-bone POSIX threads and many other things. So the programming models for shared memory keep popping up every week almost, so you can choose. For distributed memory, MPI is probably the only choice that you have. PGAS models keep coming in, but none of them has actually taken on any speed, so MPI is probably the best bet if you do some new development today. And of course, you can combine shared and distributed memory with pure MPI, MPI plus OpenMP, and MPI plus any shared memory model, and even MPI plus accelerators. Whatever you choose as a programming model, and this is true, you never have any good grasp in the model on the topology features. There are some features of topology that are coming in to MPI and OpenMP slowly. So OpenMP4 and MPI3 have some topology features. Like in MPI3, you can have communicators that span one node, which is good because you have a topology feature in the programming model. In OpenMP4, you have a notion of topology and pinning, but we will see how that works out and how well that can be used in practice. All those models require an awareness of topology and affinity. So you need to know where your threads and processes are running and what are the requirements your program has on the hardware to judge where your threads should be running. So So you have to think about that to get the best performance out of a machine. One simple example, MPI. In MPI, the programming model is like this. I have processes with attached memory. These processes run on processors. And the fact that some of these processors might actually share memory is hidden by me, is hidden by the abstraction layer MPI from me. So I don't see that these two might actually be in the single shared memory. So when I do some communication between two processes, what I see on the programming model level is a communication via some network. Okay, that's all I see. In practice, they might be on the same socket and share probably an outer level cache, which makes communication potentially easier and faster if the MPI library knows about that. Modern MPI libraries do that. Okay? If you have a modern MPI library and your two processes you want to communicate between are on the same socket sharing a cache, then the MPI library behaves differently. Modern MPI implementations do that. But still, it's different in terms of performance, of course. They could be on different sockets in the same shared memory node, or they could be on different nodes altogether. And of course, all these communication paths have different properties in terms of latency and bandwidth. So topology impacts the performance of your communication paths. And it's not easily visible in the programming model itself. You have to think about that yourself. With OpenMP, we have a similar effect, and we come to that later, probably today. So in OpenMP, we have this fork join model of parallel execution. We have a master thread, and it forks into threads. We have a parallel region, then a serial region again, where the worker threads are sleeping. And then we have a parallel region again with a team of threads, which could be smaller or larger than before. And also, the typical performance properties of this kind of parallel execution depend on the topology. For instance, if I have to synchronize threads using a barrier or a lock or some kind of synchronization primitive, then if I do that with two threads sharing an outer level cache, that's potentially much faster than doing that with two threads not sharing a cache. So the synchronization must be done using the main memory. Modern standard processors do not have any hardware facilities for synchronization. Everything is done in software. So if you have to synchronize all the 8 cores, it's a software thing. There's no wire or anything going through the machine, making it easy to synchronize those cores. It's all in software. And you will see that this makes a huge difference in terms of overhead, whether you have threads synchronizing on a shared cache or on separate caches. And of course, the whole thing gets probably completely out of hand if you want to combine MPI and OpenMP or MPI and any shared memory programming model. So here we have a cluster, 2 nodes. Each node has 2 sockets. Each socket has 4 cores. And there are lots of choices in the first place how to distribute your processes and cores and threads. So for example, we could run 1 MPI process per node with 8 threads, like this. You could run 1 MPI process per socket, and each socket runs 4 threads. You could run the same number of MPI processes, but distribute the threads that belong to 1 MPI process round robin across the sockets. So M0, T0, that's the first thread of the first process, is here. M0, T1, that's the second thread of the first process, is here, and so on. So you distribute the threads round robin across the 2 sockets so that the 0 thread of either process is located on the left socket. Probably that's better for your application. Yeah? We have to know. And then you could run 2 MPI processes per socket, that's 4 per node. And then again, you have choices how to distribute the threads. So lots of choices. Whatever you do, be aware that the position and the choices that you make here impact the performance of your code in many cases. Yeah? Some codes don't care, but this is the minority. Many codes do. And you have to have some tools to enforce this kind of behavior. Whatever you want to do, use a tool that allows you to enforce the desired behavior. And we will show you something that can do this. Okay, so that's our conclusion slide about architecture. Modern computer systems have a rich topology, meaning we have shared and separate resources, shared and parallel resources, which you have to think about. We have hardware-level parallelism on the socket level, so we have cores, CPUs, GPGPUs, probably several of them in the node. We have SIMD-level parallelism between 2 and 8-way, probably 16-way parallelism today. And on GPGPUs, the SIMD parallelism is much wider. So the SIMD unit is probably 1 SMX on Keplers, or 1 warp, probably that's 32 cores. And we have superscalarity, meaning we can execute many instructions in each cycle between 2 and 6. Usually 4 is the practical limit. Exploiting performance means you have to use all those parallelism, and you have to be aware of the relevant bottleneck. As we said in the beginning, high-performance computing, when done right, is computing at a bottleneck. Usually there is, for each loop in your program, there's an identifiable bottleneck. Probably it's a pipeline stall, because you have some dependency in your loop. Probably it's memory bandwidth, very simply. Probably it's, if you're lucky, the peak performance of your add pipeline. And that's good, because you're computing at the highest possible rate. If you do that, if you can do that, that's fine. You can stop optimizing, so to speak, yeah? At least in this, at this issue. The performance of programs is sensitive to architecture. Because we have this topology, you have to think about architecture in relation to what the requirements are of your program towards the architecture. So we have topology and affinity issues. Standards do not contain many topology features. It's creeping in, but it's slow. Okay, so you're still required to use external tools or external facilities to enforce the affinity awareness that you want. Okay. That's it for the architecture part. I will switch immediately to the next lecture. So now that we know a little bit about computer architecture and what's important in architectures, we can go back to the beginning and ask, why do we think about performance the way we do? Why do we think that modeling performance, thinking about performance in terms of models is so important, and why is it useful? Many people think, I can't make a model about my program because it's so complicated. It's true that there are some programs, some setups which are complicated and which cannot be cast into a model, which cannot be described in a model. On the other hand, most scientific simulation codes, whatever region, whatever field you're looking at, can be described by simple performance models. So there's no silver bullet. You can't catch it all, but you can catch 90+%. That's the thinking. So why care about program performance at all? Of course, you all know why we should do that. Of course, we want to win the Golden Bell Award, the Gordon Bell Award. Of course not. We want to solve problems faster, or we want to solve larger problems in acceptable time, whatever that means. Yeah? Could be overnight, could be over the lunch break, over a cigarette, whatever duration of a PhD thesis. How do I know that performance is good? And many of the things we're dealing with in this course target this question. How do I know whether performance is good? How do I know that the light speed of the program and the hardware is actually achieved? It's not good scalability across cores. We showed this in the beginning. Good scalability does not imply that you're hitting the relevant bottleneck. Actually, if somebody says that their code scales up to 1 million cores from 1 to 1 million perfectly, it's very suspicious. I usually don't believe that. I believe that it's scalable, but it's easy to scale, as we saw. Is high fraction of peak performance a good indication? Probably. If you get a high fraction of the theoretical peak performance of your machine, like 90% of the peak, that probably means you're doing matrix-matrix multiplies again and again with large matrices. That might be good, might be an indication that it's good. But on the other hand, it's very easy to get a high fraction of peak performance. Just put in more arithmetic. Just put in a variable that you're adding something to, 0, every cycle. So it's very easy to get a high fraction of peak performance. So we have to think about what is the relevant, the useful work in my program. And if I only count that, do I then get a high fraction of peak performance? Okay, that might be an indication. The actual factor that you have to consider is that the code execution hits the relevant bottleneck. If code execution hits the relevant bottleneck, you're done. And then you can think about, what can I do to my code? Okay, is there something I can do to the code to circumvent that bottleneck, to make it less relevant, to reduce the pressure on this bottleneck? How do I know what the bottleneck is? I do a performance model, and I compare the model with my measurements. And if the model and the measurements coincide, and we will see what that means, coinciding, then I can be almost sure that I understand what's going on. What should be modeled? We should not model the ability of a programmer or a framework or a library or a compiler to generate efficient code. Yeah? That's not the point. Of course, we need all those tools. We need a good programmer. We need a good compiler to do the largest step. But then, in the end, we have to check, is the implementation I get on the lowest level compatible with the hardware? Does it hit the relevant bottleneck? Another way of modeling, and this is actually quite popular, is to measure or model the impact of a set of hardware metrics. So for example, you have a complicated program, and you have a tool that gives you all these interesting hardware metrics, like cache misses, and sometimes also cache misses, because that's what people usually look at. And you can prove that the level 2 cache misses are most important for the performance of your program. Okay, yeah, that's an interesting fact, but it doesn't help you understand what's going on. And you will see that measuring cache misses is not what you should do in the first place to get an understanding of what your program really does. What you want to actually probe is the performance of the implementation of an algorithm on a kernel level, loop by loop, solver level, several loops glued together to make a complex, get a complex thing done, and the application level ultimately. Yeah? Sometimes you have to stop along the way. I mean, there are applications which are complicated, where the runtime is distributed across hundreds of kernels. This is really hard. Okay? And then in terms of hardware, first we start always on the compute node. We start on the core, in the chip level, in the node level. And if we understand the performance there, we can go on and extrapolate to the network and the full system. I already indicated there are two ways, two approaches to do modeling, and we call it the black box and the white box approach. And I don't want to bash anything. I just want to say that we're doing the white box approach. The black box approach is we determine, for example, this is just examples how to do it. We could determine the utilization of processor resources, network file systems at runtime. So we monitor the running application. We determine the performance of an application using different input sets, different hardware probably also. We determine the correlation of certain hardware metrics with performance behavior. So I could identify, okay, this metric, for example, TLB misses, is not important for my performance, but L3 cache misses are important for my performance. Okay? This is something that drops out of the process. It's not something you put in. And finally, you could do some automatic tuning. You know that you have a lot of parameters and a huge parameter space to scan for some optimization approaches. Okay? So for example, if you do standard optimizations like unrolling and blocking, there's many parameters that go into this. How do you choose those parameters? You could, and there are many auto-tuning frameworks that help you with that scan a huge parameter space and give you the point in parameter space where the performance is best. Okay. The main point about this black box approach is that people try to do it automatically. It's always a target to automate this process so that knowledge of the application is not actually required. You do it automatically. The white box approach is different. We set up an analytical performance model for a given algorithm or kernel. So we always start at the loop kernel on a given architecture. We use hardware counter measurements. So we use tools to validate the model. So for example, if our model predicts that for every flop that we do, we have 24 bytes of data transfer across the memory interface, that's something we use in the model. We use hardware performance counters to validate this. We measure this value, and if it coincides with a model, we're fine. Yeah, we are satisfied. If it does not coincide, we learn something more. And then, if we have a valid model, we identify optimization opportunities and start all again. Now, this division into black box and white box performance modeling is not new. It's not our invention. Others have told us for a long time. This is a slide from Darren Kerbison from Pacific Northwest National Lab. They had a successful series of tutorials at supercomputing conferences a couple of years ago. And here also they compare performance modeling in the Blackbox variant versus brand X, which is the Whitebox variant. And I want to point you to this comment here. In the performance modeling using a Whitebox approach, so analytical performance modeling that takes into account the architecture and the interaction of architecture and code, if your model and your measurement disagrees, if your model is wrong by some amount, too large amount, this challenges your assumptions and yields new insights. So you have to look into it more deeply. You have to think about, what have I done wrong? Okay, what's the problem? Probably I've overlooked some hardware feature that kicks in and I haven't considered in the model. Probably I have miscounted some things, like data transfers, flops, or whatever. So it challenges your assumptions and gives you new insights. In the black box approach, if the model doesn't work, it's only an indication that the framework is limited. And there's no new insight gained. And that's probably the biggest point, the most important point you want to make. Since we're physicists, we like to play with examples from physics. I think there are some physicists around. Who's physicist? 1? Okay, 3. Very good. Good fraction. In physics, you have a very similar situation. People don't believe that this is an analogy, but it's very good as an analogy. Everybody knows Newtonian mechanics. You learned it in school. Force is mass times acceleration. And you can describe interesting toys with it, but you can also describe the movement of galaxies and of comets and planets. Yeah? People have discovered planets which haven't been observed before using only Newtonian mechanics. However, we know it's wrong. Newtonian mechanics is not the correct picture of nature because it fails at small scales. If you look very closely to a hydrogen atom, it's not little spheres bouncing around. We know that we need a different kind of physics to describe features which happen at very small scales, like the hydrogen atom. And here we need Schrödinger's equation. Now, it is possible to come back from Schrödinger's equation to Newton's equation of motion, but you don't want. You don't want that. You know when this should be applicable and you apply it. And you know when this should be applicable and you apply it. So in most cases, this is sufficient. Newton is okay. But then we know, even if we go to Schrödinger and can solve the hydrogen atom and more complex stuff, it's still wrong. Because what actually happens is something more complicated, which has to do with space-time symmetries. And this is relativistic quantum field theory. And still, you could describe decays of particles, for example, collisions of particles, conversions of particles into each other. You could come back from this to this and even to this if you wanted. You don't want to, because the day-to-day effects that you deal with in your daily life are governed by Newtonian mechanics, probably quantum mechanics, because everybody uses a smartphone today, and this is, of course, a quantum mechanical device. So what's the consequence? If a model fails, we learn something. That's at the heart of physical modeling. If a model fails, we get something new, something interesting, insight. And a simple model can get us very far before we need to refine. And that's our thinking. And you can, surprisingly, modeling approaches work very well also in computer science. We've promised that we are going to describe a so-called performance engineering process. And we will see that this process can be carried out. And we show you parts of this process along the 2-day lecture here. This process usually starts with getting to know your code. And getting to know your code starts with a profile, runtime profiling. How much time is spent in every part of the code? So what are the important routines? What are the important loops? If you do that, you identify the important loops in your program, and you look at them. So you say, okay, this loop has a couple of flops, it has a couple of loads and stores, so I do a code analysis. How much resources does this loop require? What kind of computation, what kind of data transfer. I do an algorithm code analysis. This is yet independent of the hardware it's running on. It's a pure code analysis. It's just getting to know the code better. And then from this, I want to construct a performance model. I know from the code what it should do, what kind of data transfers and work it should incur. And I need a performance model that gives me an indication how fast it will run. But I can't do that on this level. I need more input. And the additional input I need is, first of all, machine characteristics. So for example, if my code does a lot of flops, if there's a lot of computation, I want to know what's the fastest rate of computation I can possibly get. That's a machine characteristic. I can look that up in the vendor documentation. Another potential bottleneck is the memory bandwidth. I could look that up as well, but usually you don't get the full memory bandwidth on a real system. For example, in Intel systems, if you look at a single socket of a modern server processor, you get between 80 and 85% of the theoretical maximum memory bandwidth. So that's something you probably have to measure, and that's what we call kernel benchmarking. If there's some stuff we don't have documented in the vendor documentation, we have to measure it. Okay? And using these inputs, we can construct a performance model together with the analysis of the algorithm and the code. Now, if we have established a performance model, we can compare it with reality. Probably it's good, probably it's wrong. If it's wrong, we have to go back to the drawing board and see if any of these inputs were probably wrong. But even if it fits the performance we measure, there's still some slight doubt, because I could have made two mistakes that cancel each other. I get the right performance number from my model and from the measurement, so they coincide, but it could be canceling effects. So I use hardware metrics and code traces to validate my model. For example, I count how many flops are actually done. I count how many cache lines are transferred between the cache levels. I count how many bytes are transferred per flop between the memory and the CPU. And if these numbers coincide with my model, because they are in the model, then I'm pretty sure that I have the right image of what's going on. Okay? So we use traces and hardware metrics to validate the model. And then if I have a working model and my code behaves accordingly, I could think about code optimizations. Ameliorate the bottleneck, lift the bottleneck, reduce the pressure on memory interface, for example, or try to use SIMD execution to speed up the execution of the core, things like that. And then if I've changed my code after the optimization, I go back to the runtime profiling and deal with the next loop that's interesting or important in terms of execution time. Okay, so the performance model in this cycle is the central component. And if it fails, you learn something because you have to challenge your assumptions about code execution. That's the basic thinking. What do we have to know? Actually, it's all already in the diagram in the previous slide. You have to know about the hardware structure, node architecture, chips, sockets, SIMD units. You have to know about the basic limitations. So how much work can the hardware do, possibly, per cycle, per second? These are things you have to know. You have to know the basic requirements of the code, so which bottlenecks may apply, and there are some typical performance patterns that are easily identifiable. We'll see some of these, for example, pipeline hazards, or memory bandwidth limitations, or peak bandwidth. And we have to know about the performance properties of typical programming models. So most of the things we show you are independent of the programming model. They are completely between the software, the loop code, and the hardware. But some things are specific for certain models. One example which we will see is synchronization overhead for OpenMP loops. As you probably know, every OpenMP loop has an implicit barrier at the end, which is a good thing, because you have correct code, probably. And this barrier costs something, and it's important to know how much it costs. Okay, so much for the performance engineering process. As I said, we will highlight some parts of this process as we go along, and you will be able to identify it. Okay, so I think we've motivated why it's important to think about topology and affinity. So where does my program actually run in this hardware? And the next question is, how do I enforce it? How do I make sure that the hardware is utilized in the way I want it to be utilized? And how do I know about the topology in the first place? First of all, I need to know what the topology of my node is. So how is it laid out? How many sockets are there? How many cores per socket? Is SMT turned on or not? Things like that. And there are some tools you can use, which are available on any Linux system. And there are some tools we have developed which can help you with that. So again, topology is where in the machine does core number n reside? Nowadays, we should rather say hardware thread number n, because usually one core means several hardware threads, 2 to 4 nowadays. Which cores share cache levels, and which hardware threads share a physical core. Now, if you're in Linux and you don't have anything else to work with, you could just type cat proc CPU info. You get a huge listing, which is a little bit cluttered, not easy to read. We will also see that sometimes the information is a little bit, not wrong, but badly structured. And the point also is that the numbering of the cores in the node might change if you go to another node, which has probably the same hardware, but a different BIOS or different Linux kernel. So this numbering might change. You can use the NUMA control tool. This is actually quite nice. If you say NUMA control -- hardware, NUMA control is part of the NUMA tools package, which is part of any modern Linux distribution. If you say NUMA control -- hardware, it gives you this listing. Here we have a shared memory system with 4 nodes. Nodes in this case meaning CC-NUMA nodes, CC-NUMA domains, memory domains. Each memory domain has 6 cores. We have domains 0, 1, 2, and 3. And each domain has 8 gigabytes of memory installed. And in this case, in the first domain, there's 4 gigabytes left. In the second domain, there's nothing left. And the other 2 domains are empty in terms of memory utilization. And you also see the association of core IDs to NUMA domains. So 0 to 5 are node 0, 6 to 11 are node 1. Then 18 to 23 are node 2. So it's not consecutive, as you see. And this is also quite an interesting and important thing to see already. It's harder to obtain information on the caches. So how large are the caches? What's their associativity level? Yeah, and things like that. There's no ready-made tool that gives you this information. And that's why at Erlangen we have developed the LIKWID tool suite. LIKWID stands for like I knew what I'm doing, expressing the fact that you know what you're doing if you employ this tool suite. It's open source. You can download it from Google Code. There was a paper describing the main features. You can read about the gory details. And it contains a lot of tools today, and we can only highlight a couple of those, the most important ones. The thinking is that we actually don't need complicated tools to analyze code behavior and to care for proper code execution. Simple tools will do it. It's a little bit like the Unix thinking. Yeah? Make simple tools, many of them, glue them together and to reach your goal. There are complicated tools which you sometimes need to analyze performance behavior, but in many cases you get along with very nice and simple tools, and LIKWID is one of these tools. Here's a list of tools. It's continuously extended whenever we think of some nice feature that justifies inventing a new tool for it, we add it. You will see something of this later. So the first one I will introduce is LIKWID topology. LIKWID topology gives you all the knowledge you need about the node structure, how many cores, threads there are, caches, and so on. So interesting things about the hardware. LIKWID pin allows you to enforce affinity constraints. So you can enforce certain threads of your hardware, of your threaded application to run on certain parts of the hardware. So they stay there. Okay, so you can enforce the affinity you want to employ without touching the code. And it works for any threaded programming model that builds on POSIX threads. Okay, if you do something else, then it doesn't work, but everything that works with POSIX threads will do. LIKWID perf counter is a tool that can measure performance counters. If you've ever worked on an SGI system, you probably know tools like libfpm on Altix or perfx on the old Origin systems. This is similar. It was motivated by this. LIKWID MPI run is a wrapper script that tries to give you an abstracted view for starting hybrid MPI OpenMP programs. So starting a hybrid program is not that hard. You have to compile your program with MPI plus OpenMP. You have some parallel loops. Then you start it. But if you don't do anything special, you don't know where all those threads are running in the node. And LIKWID MPI run tries to give you an abstracted wrapper layer that you tell it, I want to run 1 process per socket, 6 threads per socket, and do it. And then it does it. Okay? This is not very well tested, so we are really interested in getting more users to work out the bugs. Liquid Bench is a low-level bandwidth benchmark generator tool. We will see later in the lecture how important it is to do low-level micro-benchmarking, and Liquid Bench is a tool for that. And there are some more tools which are not so interesting. Okay, liquid topology. Here's an output of liquid topology as we get it on a Cray XE6. This is Hermit in Stuttgart. I think there was an XE6 here before. You see the CPU type is printed. It's AMD Interlagos processor. Each node has 2 sockets, 16 cores per socket, and 1 thread per core. So we see immediately there's no hyperthreading such things enabled because AMD doesn't support that. And then there's a list, a table of hardware threads going from 0 to the highest hardware thread ID you get, in this case 32. Then for each hardware thread, we get the thread ID, the core ID, and the socket ID. Of course, the thread ID is always 0 because we only have 1 thread per core, no SMT. We have, for each socket, we have 16 cores. So it goes from 0 to 16 on the core list, and socket goes from 0 to 1. So this is actually already a quite complete picture. If you know what a socket is and what a core is and what a thread is, you can make sense out of that list, but it's not very easily digestible. So we present this information in other ways later. We also see here a listing of which cores belong to which socket. So 0 to 15 are on the left socket, and 16 to 31 are on the right socket. Then there's a block about cache topology. We have the level 1 cache. It's 16 kilobytes of size. And then we want to know which cores in the machine share a certain cache level. Because a shared cache level is a shared resource, which might constitute a bottleneck. So that's an important piece of information. In this case, we see here a list of so-called cache groups. Each list of numbers in brackets is a cache group. And we see these lists are only length 1, which means every single core in this machine has its own level 1 cache. And we have 32 of them. So we have 32 times 16 kilobytes of level 1 cache aggregated across the whole machine. Level 2 cache has a size of 2 megabytes. That's always one chunk. 2 megabytes. And the level 2 cache is actually shared between pairs of neighboring cores. So core 0 and 1 have a common level 2 cache of 2 megabytes. And we have 16 of those caches. So there's 32 megabytes of level 2 cache in this machine. And we have a level 3 cache of 6 megabytes. And it's shared across 8 cores. So we have 4 times 6 megabytes. That's 24 megabytes. And this is strange about this machine. It's in the hardware architecture. You have, on this machine, if you look at the complete node, you have more level 2 cache than level 3 cache. There's more to be said about level 3 cache. Whoa, that's not good. Oh. Sorry, I have to put in the batteries. Robust, okay. Perfect. Must be Swiss made. Okay, so we have more level 2 cache than level 3 cache on this machine. And we'll see more about the architecture of the L3 cache or the performance properties of the L3 cache on this architecture. Then there's a block about NUMA topology, and essentially it's the same output that we have when typing NUMA control -- hardware. Yeah? It says we have 4 NUMA domains. Each domain has 8 cores in this case. Each domain is equipped with 8 gigabytes of memory, and we see how much of this memory is free. And in the end, that's the consequence of using -G for graphical. Now, it's not really graphical, but it's ASCII art, but graphical enough to get a good overview. This is, again, a view of the complete machine. You see socket 0 and socket 1. In each socket, we have 2 chips, 2 separate chips, each with its own 6 megabyte level 2 cache. Okay? And you see nicely the numbering. You see the sharing of the cache levels. We have one 16 kilobyte cache for each and every core. And we have a 2 megabyte cache shared by neighboring cores. AMD calls a pair of cores a module. And actually, they also share the floating point unit on this architecture, which is important knowledge that you don't get from liquid topology, but you have to know. So optimize your code. Okay, so that's liquid topology. If you add the -C switch for cache, you get more information in the cache sections. For example, you see how many sets you have, how many ways each cache has, things like that. Cache line lengths and so on. Okay. Now that we know how the machine is laid out, we want to use this knowledge to enforce the affinity for our programs. And there are some standard tools, again, that you can use, which should be available in any system, on Linux and in similar ways on other systems. And there's Liquid Pin. On Craze, you have AP-Run, which does it all in a neat, very nice interface. So if you're happy enough to have a Cray, that's fine. If you don't have a Cray, you have to do something else. Just as a motivation, why affinity and pinning is important. I mean, you should know by now that it is important, but we haven't actually shown any substantial data to support this. We have made a little experiment here. There's a 2-socket Sandy Bridge node, 8 cores per socket. We have 2 threads per core, so hyperthreading is enabled. And we make a simple experiment. We run the stream benchmark, which probes the memory bandwidth available on the system. And we scale the number of threads for the benchmark from 1 to 32. We have 32 hardware threads in this machine, 16 physical cores. And if we increase the number of threads that execute this benchmark, we expect some behavior, probably. No? You understand later what the behavior should actually be. Now, if we switch off all pinning mechanisms, so we allow the compiler and the operating system to deal with the pinning by itself. Do not enforce anything. Switch off all automatic and explicit pinning mechanisms. We get this behavior. So this is performance. The stream benchmark reports performance as a bandwidth number, so how many bytes per second are transferred. Higher is better. And this is the number of threads, so we're going from 1 to 32. And we see that if we go from 1, so for 1, we have a very specific performance value, no fluctuation. And then we have these whiskers, so this is min-max and 75 and 25% percentile and the average. So we see there's a lot of fluctuation. Even with 2 threads, we have about 20–30% fluctuation in the performance when running this benchmark multiple times. We run it 100 times, and there's a lot of fluctuation. And the more threads we use, up to 16, the more fluctuation we get. And with 16 threads, we almost, not quite, but almost get 50% factor of 2 fluctuation in the performance. And then we go to 17 threads, and performance goes down, but also fluctuation goes down. And only if we fill the complete node with 32 threads, we go back to a high performance level and just a little fluctuation. Okay? So if you want to take out this variability of your in your performance measurements, you have to think about pinning, affinity enforcement. And that's what happens if you pin. So here what we've done is we fill the machine gradually with threads. So we do 1 thread on 1 core, 2 threads on 2 cores, and so on. So we fill 1 socket first, only using the physical cores. So if you run with 8 threads, it's the 8 physical cores of the first socket. And we see a typical behavior, which we will recover many times in this course. It's a typical saturation behavior. So with 1, 2, 3 threads, the performance more or less scales by a factor of 2 and 3. But then, starting with 4 and 5 threads, we saturate. And using 5, 6, and 7 threads, we don't get significantly more performance because we hit the memory bandwidth barrier on this level. Okay? And then, with 8 threads, there's no fluctuation. We have about 40 gigabytes per second. That's what this node can deliver per socket. And then, we use 9 threads, 10, and so on, up to 16. And this is the second socket. So with 9 threads, we use the 8 cores on the first socket plus the first core on the second socket. And you see the behavior is linear up to the point where we get 16 threads on 2 sockets, and this is 80 gigabytes per second, so it's perfect scaling. If we go from 8 threads on 1 socket to 16 threads on 2 sockets, we get a factor of 2 of speed up. That's what is expected because we have a CC-NUMA system. A CC-NUMA gives us twice the memory bandwidth for 2 sockets. Is there anything strange about this behavior? Why? Mm-hmm. Okay, so you've spotted it. The problem is we have this nice saturating behavior here, which is completely understandable. Now, the code is just too fast. It exerts too much pressure on the memory interface. It cannot be, the units cannot be saturated by the memory interface, so it saturates here. And then if we use the second socket in addition, we get linear behavior. So why don't we get a second hump like this? Why don't we get a second saturation shape? Why do we get saturation on the first socket, but as we extend to the second socket, it's linear scaling? Some people would say, okay, why care? Linear is good, so go ahead. But we want to understand what's going on. So why do you think that is? Any ideas? Also one of the interesting patterns. There is a barrier, of course. So we have a parallel region. This is a for loop, doing this benchmark, reading a couple of arrays from memory, doing some multiply add, and writing something back. And in the end, there's a barrier. But why is the barrier important? A barrier is important. It's actually the main thing. But why is it important? The barrier takes more time because more processes. That's true, but it's not an issue. Because the benchmark runs for seconds, the barrier takes microseconds.
The barrier would be infinitely fast the same.
Yeah. If you had a perfect barrier, zero cycle overhead, get the same picture. It's not the overhead from the barrier, but the barrier is the key thing. Think about what happens if you run with 8 threads. So one additional thing I have to mention that there's static load balancing. So we use a normal static schedule. Each thread gets the same share of work. Okay? And they all synchronize at the end of the loop. So think about what happens at 8 threads. Each thread gets the same work, 1/8 of the complete chunk of work, and it's saturated. So each thread gets 1/8 of the memory bandwidth. Now we add a 9th thread. The 9th thread is in the second socket. It gets the same share of work as the others. So every one of those 9 cores gets 1/9 of the work. The first 8 share the left memory interface. So they are seriously bottlenecked. Okay? Each one of those 8 threads gets only 1/8 of the bandwidth. But the 9th thread, which has the same share of work as each core in the first socket, is on a socket on its own. It has the same work, but it's on its own socket. So its share of memory bandwidth is much higher. It's faster. So this 9th thread sitting here has the same work as any other thread sitting here, but it's finished much earlier because it has more bandwidth, more room to breathe, so to speak. So it finishes early, and what does it do? It can't do any useful work because everybody synchronizes at the end. So it has to wait. It has to wait until all the others, the other 8 in the first socket, are finished. And then things can go on. So it is faster than the others, but only for a fraction of the time. And the rest of the time, it spends waiting, spinning in the loop, in the barrier. So on average, everybody only gets the same performance again. Everybody gets 1/9 of the final performance. So what we get here is a speed up. Here, this speed up we get from 8 to 9 is exactly 1/8 of the performance of 8 threads. Yeah, because we have a speeder, we have a load imbalance imposed by the final barrier. One thread is faster, it has to wait, and on average, everybody has the same performance again. So we're pulling the brake, so to speak. And of course, this occurs to any situation up here until we have 15 threads. But with 16 threads, we have a load balance again. With 16 threads, every thread gets the same amount of work. Every thread has the same share of the bandwidth, because we have now the same number of threads left and right, and then we have perfect scaling. We could remedy this, yeah? Sorry?
Why don't we have the same shape of the curve progress from 9 to
That's what I was explaining. So if you add another thread, it is faster by a significant amount than any thread here on the left socket. But it finishes early, but it has to wait until the final barrier. So its actual performance, end-to-end, work divided by time, is not better than the performance of any of those. So we only get a speed up of 12.5%. The average performance of every thread is the same, because they all have the same work, and they end at the same time. If you could fill this wasted time up until the barrier with useful work, we would see the two humps. For example, if you use dynamic scheduling, assuming that dynamic scheduling doesn't have any additional overhead, which it has, so we ignore that. If you use dynamic scheduling, then any thread that finishes early will get a new packet of work, and they will all be dynamically balanced. If you use dynamic scheduling, you get two humps. You won't, because dynamic scheduling has its own problems, but yeah.
And what if we just increase the amount of work for each thread? We now have 60 threads in our case, and if we increase the amount of work, we will face the same problem as the memory.
For this benchmark is made in the way that the bandwidth is the bottleneck. So the working set is always large. The standard working set, I think, is like 400 megabytes. So it's always beyond any cache size. It's always memory bottlenecked, because it's the purpose of this benchmark to probe the memory bandwidth. So if you increase the working set, you will get exactly the same behavior. So if you increase the number of threads,
If you increase the working set on 9 threads by a factor of 2,
yeah. So if you hand balance the computation, yeah? That is possible. Yeah.
9 threads that use twice as fast as the other one average. So you will get twice the work. You will run the same time, but you do more work during the same.
And you can imagine how complicated that gets if the topology is more complicated. Up to 16, we've been dealing only with the physical cores. But now beyond 16, we also have the virtual cores. So each physical core can run 2 threads. And imagine an AMD processor. It has 2 cores per module sharing a level 2 cache. It's a similar situation. So things get very complicated. So if I scale beyond 16, performance drops, because again, I have this load imbalancing problem. I have now 9 threads running left and 8 threads running right. Each has its own, each has the same amount of work. So this socket, of course, takes longer to do its work. That's why the performance drops. Again, we have a load imbalance. And only if we fill the 2 sockets completely with virtual threads, we get almost the same performance back. Mm-hmm. Yes, you would. If you fill the sockets alternatingly, so 1 thread, 2 threads, 4 threads 2 by 2, 6 threads 3 by 3, you will see a more linear behavior in the beginning, but you will see the saturation. No? You will see it not with 4 threads, but with 8 threads.
So what's happening is that you're bending off earlier, whereas if you had a linear increase, you would have seen it as you expected later on.
If you do the round-robin schedule, you would see it later on. Yeah, it would be the same bottleneck. We try to always to do it like this because it exposes the first bottleneck first. Okay, it's a choice, of course.
It's actually 1 because you've already done your already curved off.
Yeah, that's right. So it would go up here and then stay constant. Of course, this is an indication how to run codes that behave similar to this. So if you have a code that's strongly limited by main memory bandwidth, you might end up in a situation where it's useful to run 4 or 5 threads and then leave the other just idle. You save power, you save energy. Probably you're doing something good for your communication properties because you have less processes, less threads. So yeah, this is a good thing. Okay, so as you see now, there are several reasons for caring about affinity. You want to eliminate variation, of course. You may want to use architectural features like shared caches. So if you want to make use of a shared cache for communicating between processes, you have to make sure that these 2 processes which are communicating are on the shared cache. And you want to avoid resource contention, like bandwidth bottlenecks. For example, by running 5 threads left and 5 threads right to get the maximum performance with the least amount of threads. Yeah.
Is this affinity you're doing or pinning?
We use the two synonymously, so it's the same thing.
So, because pinning usually, as I understood it, has groups of cores. Affinity is specific.
We mean the same thing by both terms, affinity and pinning. So you make sure that a thread runs on a specific core and it stays there. Okay, so how do we enforce pinning? There's a tool which is available also on all systems. Linux systems, it's taskset. It restricts the movement of the threads of a process. So you can say, I give you a mask, probably a bit mask, or a list of cores. For example, you can use it like this, taskset minus C4, and then some process ID. And this makes sure that all the threads that this process 33187 generates are restricted to core number 4. You could also use a list of cores, 4, 5, 6, 7. That's a good thing, but it's not enough, because if you specify more than one core, the threads can still move within the set. So it's only a restriction, it's not a pinning. It's just it restricts the movement of the threads, but it does not pin each and every thread to a specific hardware resource. Of course, you can do it the hard way and use an API. In Linux, this is called set affinity. You can give it a process ID. If you say 0, it means myself, my process ID. You have a length and then a mask, and every bit which is set to 1 in this mask indicates that the threads, or that this thread, can occupy this core. Yeah? So if the mask is only 1 bit set, you restrict the thread to a specific core. That's how you do it on a program level. Of course, that only works on Linux systems, and it's not really compatible with porting your program. Yeah? Because if you port to a different machine with different topology, you have to adapt these masks. You don't want to do that. You don't want to put these hardware specifics in your code. And if you're on a shared machine, yeah, for example, if you only get half of an ultraviolet SGI machine, then you don't know what to do, because you don't know which core IDs are yours and which are your neighbors. Another tool, complementary, is NUMA control. It's very similar to taskset, so we'll skip it. And of course, if you go to other operating systems, like Windows, there are similar things. So in Windows, set affinity is called set thread affinity mask. It works the same way. Yeah. And there are some abstraction layers, like HWLock, which is part of the OpenMPI effort, and which also give you an easy-to-use interface to this affinity calls. But it's all in your program. Now, fortunately, compiler developers have realized early that it's necessary to give the developer some way to enforce affinity. And so all modern compilers can do this. So Intel compilers can do it starting with version 9.1. You use the variable KMP affinity, and it's very, very complex. So I never understood it. It's really complex, but you can do all the things that you want. For example, you can say, I only want my threads to run on the physical cores of the socket, or on all the virtual cores, or I want to leave every other core empty, things like that. Very complicated things. PGI, Pascal, GNU all have this. In SGI, there's a tool called dplace, which can do it. And OpenMP4 has some facilities for that. In MPI libraries, you have similar things, Intel MPI, OpenMPI. They all have environment variables which can influence the affinity and the pinning. And of course, if you have compatible setups, so to speak, so if you have Intel MPI plus Intel OpenMP, you can also combine it, and it works correctly if you know how to do it. LIKWID pin tries to abstract away all this variation. Of course, you can use the compiler facilities if you know that you use GNU compiler and you never want to use anything else. Okay, you can be happy. But LIKWID pin tries to ease the burden of the pinning. And it has a very nice feature, which is called logical pinning, which I think is an interesting thing that not everybody has. So what does it do? It pins processes and threads to specific cores without touching the code. And it supports all programming models that are based on POSIX threads. So if you have any threading model which has POSIX threads underneath, then it works. It is a wrapper tool. So you start your application with LIKWID pin as a wrapper. And what it does is it hooks into the pthread create call. Pthread create is the call in the POSIX library to generate a new thread. It overloads that call, intercepts it, and then it pins the new thread to a core which is given in a list. Okay? The prerequisite for this is the binary must be dynamically linked. It does not work out of the box for static binaries unless you link the LIKWID library to the binary. That's also possible. But out of the box, without touching the make process and your code, it only works with dynamic binaries. It's about logical core numbering. I said that the core numbering might change, even for the same hardware, if you use another BIOS version or another Linux kernel. And the core numbering might also be very, very awkward, so close to random. We've seen systems where the core numbering is really, really strange. And you don't want to remember that on this particular system with this kernel, your cores are numbered round robin and not consecutively. You don't want to remember this, and that's how logical core numbering helps. So here are examples. My app is my application, whatever I've written. It's an OpenMP application with parameters, and it's called with LIKWID pin as a wrapper. And if you use it like this, it's exactly compatible with task set. So you say -c, and then a list of cores with commas or ranges. And then the threads which are generated by this application are pinned consecutively to this list of cores. Yeah, in this case, it's 5, 0, 2, 4, 5, 6. And if it has 5 threads, they are pinned to cores 0, 2, 4, 5, 6. And the numbers that you give here are exactly the numbers that are printed in LIKWID topology. So there's a one-to-one correspondence. If you don't want to remember where cores 0, 2, 5, 4, 6 are in the machine, you don't have to. All you have to remember is the topology. So how many threads are there per socket, how many caches, and so on. So you can do it like this. This is logical numbering. And this says, I have 4 threads. Please pin them to the first 4 physical cores on the left socket, socket 0. No matter what the actual numbering is. So the numbers of these cores in the original numbering could be 0, 8, 1, 9, 3, 10. Yeah. Here, we don't have to remember this. We just say socket 0, physical cores 0 to 3, and that's it. No matter what the physical numbers are. So here's an example how you execute it. We set the number of threads. Actually, you don't strictly have to do this. If you don't set the num threads variable, LIKWID pin will set it for you. If it detects there's no OpenMP num threads being set, it sets the variable automatically. We call stream, the stream benchmark, with a core list of 4 cores, 0, 1, 4, 5 physical cores. And you see the first output that you get is from LIKWID pin. This is diagnostic output. You can switch it off with -quiet. And it tells us it pins the main process ID to core 0. That's always done. So the main thread that's being started when you start your executable is always pinned to the first core in the list. This is core 0 in this case. Then the program starts running. The blue stuff is output from the benchmark, so from the program. And then the first time a parallel region is entered, so you have pragma OMP parallel, threads are being generated. And this is again where the wrapper kicks in. And we have here several output messages. So first of all, we get information about the pin mask. So the remaining cores in the list are 1, 4, 5. That's what's being said here. We have a skip mask of 1. I'll come to that in a minute. The first thread being generated is skipped. It's ignored. It's not pinned anywhere. This is because LIKWID pin has figured out by looking into the binary that this binary was compiled with the Intel compiler. Now, the Intel OpenMP implementation has a specific feature. If you say I want 4 threads, actually 5 threads are running. There's an additional thread, which is called a shepherd thread. It does important secret stuff, but it does not execute your code. It has administrative purposes. So this core, this thread, should be allowed to move freely around in the machine. That's why it is skipped. Yeah? So this skip mask is automatic. It's figured out by the tool. You can supply a skip mask if you know that your compiler uses a shepherd thread, but it's the last in the list. Yeah, you could supply your own skip mask to make sure it does the right thing. All the subsequent threads, 3 threads generated, are then pinned to the remaining cores in the list, 1, 4, 5. And that's it. If there's no other parallel region that generates more threads, LIKWID will not say anything anymore, because all that LIKWID does is intercept the thread creation. If there are no new threads being generated, LIKWID will be quiet. Okay, now about the logical pinning. As I said, you could have in the same hardware different ways of numbering the cores. Here, for example, you have a 2-socket system with 8 threads, 4 cores on each socket. And here in this case, the hardware threads are numbered consecutively, so 0 and 1 are on the same core, 2 and 3 on the same core, and so on. But actually, in practice, in many cases, SMT doesn't really do something good for your performance. So many people want to ignore it. So what you want to have in practice is a numbering that's more like this. 0, 1, 2, 3 are the first physical cores, the physical cores on the first socket. And 4, 5, 6, 7 are the physical cores on the second socket. So if you say 0 to 7, you mean all the physical cores, and you ignore the virtual cores. And that's the numbering we want to impose in many cases. And Liquid helps you with that. You can do that just by saying liquid pin minus C n colon 0 to 7. N colon 0 to 7 means I want to have logical pinning on the node level. So all physical cores on the node are numbered consecutively from 0 to n minus 1. And then the ones beyond 7, 8 to 15, are the corresponding second hyperthreads. So if I want to use the hyperthreads, and I want to use this syntax, I have to use n colon 0 to 15, and then 0 to 7 will be the first threads on the 8 cores, and 8 to 15 will be the second threads on the 8 cores. I can also use other prefixes, for example, 4 threads left, 4 threads right. Here, S0 colon 0 to 3 means first 4 physical cores on the left socket, and the add is a delimiter, and S1 0 to 3 addresses the first 4 cores, physical cores on the right socket. Now, depending on the topology, you could have different prefixes. So N means node, S with a number means socket, number 0 or 1 or more. There are actually 4 prefixes you can use in the current version of Liquid. N is the node. So here we have a complicated AMD Multicore system. These are 2 sockets. Each socket has 2 chips. Each chip has a common L3 cache and 1 memory interface. So if you don't specify any mask, any core list, then this is the default. It numbers all the physical cores consecutively throughout the machine. If you say S, you address a socket. And in this case, for an AMD system, a socket comprises 2 chips. If you say M, you address a NUMA domain. And for AMD, a NUMA domain is just half a chip. For all current Intel chips, a NUMA domain and a socket are the same. And C is the outer cache level. There are processors which have multiple cores on the same socket or chip, but where a fraction of these cores shares an outer level cache. So C means a common outer level cache. These are the options you have today with Liquid, and if anybody invents something new, a new layer of topology, then we can put it in here. This is very nice because it gives you an easy way, an abstracted way to access the features of your machine with pinning. But if you have many cores, like on the Intel Xeon Phi, you have 60 cores and 4 threads per core, so 240 threads. Some situations become very complicated. So for example, on the Xeon Phi, if you want to run 2 threads on every physical core, with this syntax, it's very hard. You have to compile together a very long list of core IDs. And it's not easy it's unwieldy, it's not easy to use. That's why in the latest Liquid version, we have so-called expressions. You can have compact and scattered pinning. So for compact pinning, you introduce your expression with E for expression, and then you have 2 or 4 components. Either you say thread domain and number of threads, or you say thread domain, number of threads, chunk size, and stride. So here, for example, liquid pin minus C, expression N8. This means run 8 threads on the node level. So I don't have to give it a list. I can just say 8 threads, the first 8 threads on the node, period. Gives me the first 8 physical cores. In this case, I run 120 threads, and I use the full syntax. So the third and fourth argument is chunk size and stride. I run those 120 threads in chunks of 2, in pairs, with a stride of 4. That means the whole machine is looked at with core by core. Each core has a number of threads. These are numbered consecutively. And I get pairs of 2 threads running on each core. So in this way, I run 2 threads on each core and ignore the other 2 hardware threads. Xeon Phi has 4 hardware threads per core, 4-way SMT. So this is a very simple expression compared to the huge thing you have to compile if you use it with the previous syntax. Another way of using it is with scattered placement. So for example, if you use this, -cm scatter, you set the number of threads to 4, for example, and if you say -m scatter, -cm scatter, it scatters those 4 threads as widely as possible across your NUMA domains. Yeah? So that's what we said in the stream example. That's what you get in this way. It does a round-robin placement. Yeah.
Now I see that with these expressions, I can also kind of do the similar thing as you said, using physical cores first. On the AMD, I say I want to use only 1 core bulldozer module. Is there a kind of more simple way, or do I have to use this system to make that happen?
Now for AMD, the problem is that Liquid doesn't really distinguish the special thing that we have, the 2 cores share a module. On the Intel systems, this is like SMT. The module concept is like a variant of SMT because they share a floating point unit. But Liquid sees the 2 cores as separate cores. It doesn't see it as it doesn't see a pair of cores as a topological entity. We could put it in, but it's not been done yet.
But with this one,
This will work. This includes it, yeah. You would say -e n, for example, 16, 1, 2. Yeah? Chunk size 1, stride 2. Then you would just omit every other thread, every other core, sorry. Okay, so you can play around with that. Sometimes it's nicer to use this syntax, especially if you have lots of cores. Okay, demo, very good. Just the right time. I will now try to show you a little bit about topology and pin. Yeah. Whoops. Not good. Probably. Sorry. Is it possible to have a wired connection? Because the wireless is really slow and somehow. Okay, okay. Oh, maybe we're lucky. Okay. Okay, so we'll try to demonstrate, if it's not too slow, what the Liquid topology output looks like on different machines, including the Xeon Phi, and what the Liquid pin are. Sorry. So that doesn't seem to work over the wireless. So we try to set up a wired connection, and we try to do the demo after lunch. Sorry. Okay. Then I think, should we do lunch now? I think it would be a good time, right? If it's okay with you.